Here's another example of a bending moment diagram. How to create a bending moment diagram. So what we have here is a beam. Let me just make it a straight line. So you have a beam with a few loads on it. Let's assume it's 10 kilonewton and 20 kilonewton separated by 2 meter. The beam is supported at A and B. Let's say this 2. First of all, we need to calculate the reactions at A and B. So the total load is 10 plus 20, that is 30 kilonewton. Now, in order to calculate the reactions at A and B, you take moment about either A or point B. I'm taking moment about A. When you take moment about the point A, what you have is a 10 kilonewton acting downward at 2 meter distance from A, creating a clockwise moment. A 20 kilonewton acting downward 2 plus 2, 4 meter away from A, creating again a clockwise moment, and a reaction at B acting upward, creating a counterclockwise moment when looking from A. So moment due to this force will be considered positive, and these two will be considered negative in this analysis. Or all counterclockwise moments will be considered positive and all clockwise moments will be considered negative. So what you have is RB acting at 6 meter from A. So moment about A is moment about any point should be 0 for equilibrium. So the equilibrium condition is moment about A should be 0, and the equation for moment about A is RB times 6 minus, this is a plus positive moment because it's creating a counterclockwise moment. So 6 RB minus 20 kilonewton at the distance 4 meter. So 20 times 4 minus 10 kilonewton at 2 meter. So 10 times 2 is equal to 0. That's 6 RB minus 80 minus 20 is equal to 0, or 6 RB is equal to 100, or RB is equal to 100 by divided by 6, that is 16.66. 100 by 6 is 16.67. So you've got 16.67 kilonewton RB, and we know the total force is 30 kilonewton. Therefore RA is equal to 30 minus 16.67, which is 13.33. So this is RB and this is RA. Now you have RA and RB, you can calculate the moments of this force system. Before going into calculating moment, I'm just drawing a line here so that you can draw the bending moment diagram in those lines. Okay, so I'm just leaving that area vacant so that you can do the analysis or draw the diagram there. Now the usual method is method of section. So you take a section in between each point of load application. So you take a section here, another section here, and another section here. So let's take the first section from the point B. So your first section will be just like this. RB, a section here, X, and let's call this distance X. RB we know it's 16.67, so moment about that section is RB x, and x can vary between 0 to 2 meter because the section starts here and finishes here. The total distance between these 2 points is 2 meter. At here the value of x will be 0, and at here the value of x will be 2. So you have at x equal to 0 the moment will be 0, and at x equal to 2 moment will be 2 times 16.67, that is 33.34 Newton meter. Now you take the second section between the point of application of 20 kilonewton and the 10 kilonewton force. So your section will be two here, RB here, and the 20 kilonewton load vertically downward, and your section distance is x. So the section here, and now moment about this point here. Always remember, take moment about the point where you take the section. So when you look from the section, the forces acting are 20 kilonewton acting downward creating a clockwise moment, and RB acting upward creating a counterclockwise moment. So again, counterclockwise moments will be considered positive and clockwise moments will be considered negative. So moment about section is mx is RB times 2 plus x, why 2 plus x? Because that is the total distance from the point of the section, minus 20 times x, and you have again the distance of x, or the x varies between these 2 points. Therefore the maximum distance of x is 2 at this point, and minimum distance of x is 0 at this point. So you substitute values of 0 and 2 for x. At x equal to 0 moment will be 2 RB, because this term becomes 0 and this becomes 0. 2 RB is 33.34 Newton meter, and you know these 2 points are the same because both those points are here, because in the second section x equal to 0 here, and in the first section x equal to 2 at this point. So both those points will be same, and that's why you got the same value for both these moments. And at x equal to 2 moment will be 4 RB minus 40, that is 4 times 16.67 minus 40, that is 26.68 Newton meter. Now you take the section between 10 kilonewton force and RA. So you have your beam RB and 20 kilonewton. Move it slightly towards here. 20k and another 10k, and this is your section. So you know these distances, these are 2 meter each, and this is your distance of section from the last point load. Now taking moment about the section, mx is RB times 4 plus x. Why 4 plus x? Because that is a distance to RB from this point. X plus 2 plus 2. Again, this will be considered positive, and these two moments due to these two forces will be considered negative. So minus 20 times 2 plus x, why 2 plus x? Because that is the distance to the 20 kilonewton force from the section, x plus 2, and again minus 10x, whereas x is the distance to the 10 kilonewton force from the section. So as in the previous cases, x varies from 0 at this point to 2 at this point. So the minimum value of x is 0 and the maximum value is 2. So you apply the limits of 0 and 2 for x. So at x equal to 0, moment will be 4rb minus 40. By 40, x tends to 0, so 2 times 20, that is 40, and x tends to 0, so 4rb. That will be 4 times 16.67 minus 40, which is 26.68 Newton meter, and you can see that is same as this value here. Why? Because both those values are at the same point of this point here, because the x value of 2 in this section and x value of 0 in this section are both at this point. So you have the same moment for both those values, and at x equal to 2 in the third section, 2 moment will be just substitute x equal to 2 in this equation, so that will be 6rb minus 2 plus 2, 4 times 20, that is 80 minus 20. So that will be 6 times 16.67 minus 80 minus 20, that is minus 0. So that will be 0. If you take 16.67, you will get a 0.002 or something, but you will need to consider that RB is 100 over 6. So if you substitute that value in here, you will get 100 minus 80 minus 20, and that will be 0, which is the moment at the last point at the point A. Now you can draw the moment bending moment diagram for this force system. So what you have is, you can draw it like this. So you have the point of application of loads through these lines. So just draw a straight line here. So you have a straight line, and at this point your moment is the moment of the first section, that is where is it? Yeah, this is 1, so that's 0. This is 2, and this is the same, so but still we call it 3. You have 4, 5 and 6. 2 and 3 are same, and 4 and 5 are same. So effectively you have 1, 2 and 3 are same, so therefore 4 and 5 are same, therefore 6. So these are the 4 points where you draw the values for moments. So you have 1, 0, that is x equal to 0, your moment is here 0, and at 2 you have 33.34. So you have, say, 33.34 here, and you just join these two, and at point 3, which is the same as 33.34, and the next point is 26.68. so your moment slightly reduced here. These are all straight lines. If I'm not making straight lines, apologies, these are all straight lines. So that's 26.6468. So 4 and 5 are the same, so again 26.68, and the last point is 0 at point A, so you get 0 here. Again, this is a straight line. Just bear with me if I don't make, let me make this right. So that is a straight line. Let me draw this all straight lines. One here, and you have 26 here, and you have 0 here. So this is 33 point, what is the maximum moment? That is 33.34. so that's 33.34 Newton meter, and the next is 26.68 Newton meter. 26.68 Newton meter, and you have 0 at either ends. So that is the bending moment diagram for the given force system. Thanks for watching.